So when we're finding general solutions of differential equations, it's terrific if they're in a form that we call separable. So the example that I give here, dy by dx equals 2xy, this is a situation where we can separate the variables. And let me show you what that involves. It looks like this. We will take dy by dx and we will multiply both sides by the dx. So we have dy is 2xy dx. Then I'm going to divide both sides by y, and I get 1 over y dy is 2x dx. All that is left at this point is to integrate both sides. So if I integrate both sides like this, I get that the left side is just ln absolute value y, and on the right-hand side, the antiderivative of 2x is just x squared plus some arbitrary constant. If I want to get this expression here so that it's isolated for y, I would say the absolute value of y is e raised to the x squared plus this arbitrary constant. I'm going to separate this into just simply e to the x squared times e to the c. That's just working an exponent law backwards. And then I will take that and I will say, okay, we will remove the absolute value bars on y and say that this has a plus or minus aspect to it because of the absolute value bars. E to the c times e to the x squared. And then just to clean it up a little, I might say we will let plus or minus e to the c equals some new constant, which we can call anything we want. C1, K, maybe I'll call it A. And so my final solution is y equals A e to the x squared. So this is fantastic when we are able to separate the variables, but that isn't always possible. So to give you a second example, we have the following. Find the general solution of x dy by dx equals x plus y. Now, if you cross multiply, you're going to see pretty quickly that you are unable to separate the y variables from the x variables. So what we need to do is take advantage of another strategy, which is the following. We can take our expression x dy by dx equaling x plus y and divide both sides through by this x. So we end up with dy by dx equals 1 plus y over x. And it turns out the following. If you are able to take an expression dy by dx and write it as some function of y over x, that allows you to create a separable differential equation. And here's how you go about doing it. You take the y over x and you allow it to be some variable which we will call u. Now, the other way to express that is y itself is u times x. All right. So what does that mean? That means that if we were trying to figure out dy by dx, that is the derivative with respect to x of ux. Well, using the product rule on the right-hand side, that would be u times 1 plus x du by dx, or simply u plus x du by dx. Now, we're going to use that to replace our dy by dx. That's what dy by dx is. And we're going to take u and replace our y over x. And take a look what we have when we are finished. On the left, we have u plus x du by dx equals 1 plus u. Now, I'm going to take this and try and separate the variables. Well, watch what happens here. This u and this u subtract out, so I've really just got x du by dx equals 1, or du is 1 over x dx. As before, I will integrate both sides. And what do I get from that? Well, I get, on the left-hand side, just a plain u, and on the right-hand side, I have ln absolute value x plus a constant, my arbitrary constant. Now we go back and replace u with the y over x that we originally had. So we have y over x is ln absolute value x plus a constant, and then we can just rearrange for y. So y is equal to x ln absolute value x plus this arbitrary constant times x. And that's our final answer. That would be the general solution to this differential equation. And so if we had an initial condition or some boundary condition of some sort, we could solve for the constant c. But again, I want to highlight the fact that this was made possible by the fact that we could rearrange this equation, the original equation, so it was dy by dx is some function of this y over x right here. So some function of y over x. And then we use this replacement here, that y over x is equal to u, or y equals ux. Okay, hopefully that's helpful. There are going to be some other substitutions we're going to look at in a future video that may be helpful.